going to do a couple more of those solving for an existing sine curve, a transformed sine curve. So we're going to try this one. Okay, and always read your question. Try to understand it first. So the height in meters of a nail in a water wheel. So right away, we're talking about a water wheel. And it's got a little nail sticking in it. Above the surface of the water as a function of time can be modeled by this function. So we're talking about a sine curve. Notice that this is not in front. So this is affecting the stretch of the angle. And this is adjusting the whole thing to the right. So the whole time period is going to change here. So we have to look at what the time period adjustment is. We also see that that's the axis, and there's the stretch, so that's the amplitude. Notice this minus. It's actually flipped, where t is the time in seconds. During what periods of time is the nail below the water? In the first 24 seconds. So we need to determine the period to determine if that's 1 rotation, 2 rotations, 3 rotations. So let's start with what we know. Generally speaking, on a water wheel, the center will also be the axis. So here we have an axis of water wheel, and it happens to be at y is equal to 2.5. So that's going to be 2.5 above the water. And then you can see that the stretch is 4, so you're going to have 4 up plus 4 up. So the max is going to be 2.5 plus 4, 6.5. And 4 down, so 2.5 minus 4 minus 1.5. So you can see that it goes as deep as 1.5. And if I'm going to draw the water line somewhere here, okay, it is 1.5 above that point. So since this is 2.5 and minus 4 gets me down to there, if I'm going to go down, so what's 1.5 up from there? That's where y is equal to 0. That's where y is equal to 0. So that's the old x-axis, or the current x-axis. But the old, new axis up here is above the water, which makes sense because this portion of the wheel is going in the water. Now you can also just assume the wheel's spinning that way, but it doesn't really matter. We also have to notice that this is going to be a sine curve that's adjusted left to right. So let's first figure out that period. Okay, the period is adjusted by this. So normally I would say, oh, it's multiplied by pi and divided by 4, but in reality it's multiplied by 4 and divided by pi. So if I have 2 pi as my normal period, when it gets divided by pi, it becomes a 2, and it times the 4. So that means this wheel takes 8 seconds to go around. And they want me to measure 24 seconds. So they want me to get the first time it goes in and the second time, and the third time it goes in and the fourth time. And then it wants me to get the fifth time it goes in, and the last one happens at 24 seconds right there. Now, the interesting thing is you really only have to figure out the first two, and then you add a period to each of those twice. And since the period's 8 seconds based on this, so based on this, it's 8 seconds. That means we only have to figure out the first 8 seconds and then just add 8 seconds to each of those values twice to figure out the second and the third and the fourth and the fifth and the sixth. So whenever this happens first, you add 8 seconds for the third time and 8 seconds for the fifth time. This is the second time. You add 8 seconds for the fourth time and 8 seconds for the sixth time. Become more clear when we do it. All right. So we need to know when that happens. So when is this wheel below the x-axis? In other words, when is this equation smaller than 0? Is what they're asking us. How often does that happen? Because the x-axis is 0 and the main axis is 2.5. So they're asking us, when is this equation below 0? So we can just set it to 0, and we can first graph what we know about the sine curve. So first of all, sine curve, it's going to start normally here. It would normally go up 1, halfway it's at the middle, 3/4 of the way it's down, 4 it's here. So that's 2 pi there, and that's 1 pi there. Normally it'd be 1 up, 1 down. Well, first of all, this negative, that means we're going to go down. Second, this plus 4, so the whole thing's going to go up, plus 4, and come down, and like I said, barely go under the water. So we're going to have to add a new plus 2.5 rather. So that means it's going to be here. And now if I put it in purple, it's going to go down, up, and down. And it's this part here we're concerned with. So it's clear that it's happening in the first 4 seconds, right? Because it goes down and then up. And that's the only time the water is down here. But also, keep in mind, our new period's 8 seconds, and this one adjustment, -1, actually phase shifts the whole thing to the right by 1. So now, if I'm going to do a rough drawing, I'm going to put its axis up here at y is equal to 2.5. It's going to start 1 second later. It's going to go down, up, and up. And instead of ending at 8 seconds, because we shifted 1 later, it's going to end at the 9-second mark. So I know it's going to start at the 1 second mark. I know it starts negative and goes down. And I also know the water line is down here. Well, I also know the halfway point of this is going to be 4 seconds, or sorry, plus 1, 5 seconds. I also know the quarter way of that is 2 seconds more, so this is going to happen at the 3-second mark. And I also know this is 2 seconds more, so it goes 1, 2, 5, 1, 3 seconds, 5 seconds, 7 seconds, 9. How do I know this? Because the period is 8. A typical sine curve can be broken up into 4 spots: the first quarter, the half, the third quarter, and the last half. Since I'm dealing with 8, the first 2 seconds happen here, and the next 2 seconds happen here. So I can even make a good judgment that this is going to happen around the 2-second mark, and that's going to happen around the 4-second mark. And then it's going to repeat over here and over here. And this part is not going to be in the water at all. So I already have a good estimate of what's going to happen. So let's start with the equation. So take your equation, and we're essentially going to find out when is this equation negative, or let's just find out simply when it starts, right when it hits 0, when it's equal to 0, and then we just have to figure out the next stage it comes out. And we're going to get 2 values, so we're going to take the whole equation and we're going to make it equal to 0. But the first thing I'm going to do, step 1, put the equation aside, in the angle equation. Take the internal angle transformation, everything that's happened to x, and replace it with x. Okay, that's your step 1, always. 1. Also remember, we're working in radians here, so we're going to be working in pi radians. You can think in degrees, but it's set in pi radians. So my advice there is you take this entire angle transformation of what's happening to the x value, and you just put it aside, and you replace it with x, and it makes it a lot easier. Because if you look, my sine of x, I can just treat like the angle. My sine of x is being multiplied by -4, and then it has 2.5 added to it. So to reverse the story, I'm going to subtract 2.5. So I'm going to get negative 2.5 on the left side is equal to -4 sine x. Then I'm going to divide everything by -4, so obviously sine x is going to be positive, negative divided by a negative, and it gets to be 2.5 divided by 4. It's really negative and negative, but I'm just going to change it to positive. And I also happen to know, if I look at it carefully, that's the equivalent to 5/8. How do I figure that out? Because if I multiply this by 2 and this by 2, it's 5/8. So that means I'm dealing with the fraction 5/8. Now, I can also convert that to a decimal. So notice that it's positive. So now we're going to go back to our sign, our knowledge of cast, and know that CAST, sine is positive in the first quadrant and the second quadrant. So we're dealing with the acute angle, and then we're dealing with 180 minus the acute angle. Those are the 2 angles we're dealing with, which makes sense because it happens right away. It happens before the halfway point. Okay, so that means we're dealing with a positive. We just have to figure out, is there a 5/8? Well, let's just start by taking the inverse of that and figuring out the angle in degrees. So, by the way, I'm going to write it in both radians and degrees here. So I'm going to clear my button a few times here. Then I'm going to take 5 and divide it by 8. I'm going to get a fraction. I know it's positive. And then I'm going to go inverse sine to figure out my first angle. So I get 38.68. 38.68. But I'm going to want to I want to show you that this is the same as radians. So I'm going to round up, I don't know, to there, let's say. And I actually think it ends up being that. But anyway, let's see if that would have given me the same thing in radians. What does it say that is in radians? 5, so I'm going to clear everything. I'm going to do 5 divided by 8. And I'm going to change to radians, and I'm going to do trigonometry, second inverse sine. And I get this. A weird thing. It's also equal to this many radians. Now, I don't have to convert it to this many radians right now. I can decide later if I want to do that or not, but it's that many radians. Now, how many pi radians is that? Well, let's get to that in a second. But if I wanted to convert this to degrees to confirm that I have the right thing, I would first divide it by pi and multiply it by 180, because that's how you convert. So I'm going to take that. I'm going to multiply it by, divide it by pi and multiply it by 180 and see if I get the same degrees. And sure enough, I get the same degrees, 38.6822. So that means that is indeed the radians representation of the acute angle. Now, if I wanted to just put that in pies, I would take it, and I would take the 5 divided by 8, and I would find the inverse sine in radians, and I would just divide it by pi. And this is how many pi radians it is. It's 0.2114 pi radians. And I'm going to show you that that also works. Okay. It's also equal to this many pi radians. Pi radians. And that's simply taking pi and dividing it into this first number to figure out how many pi's fit into this first number, and it's less than 1 pi. Now, I could put that as a fraction as well, but we know that this doesn't quite fraction out, so we know it's not going to be quite right. But these are all the same angle. Confusing? Yes, that's the numerical pi radians, or numerical radians, no pi, and that's when I divide by pi and I put it in terms of pi radians. And this is actually going to be what I end up dividing out with, but I'm going to work with this to show you it's the same as that. But let's find out our second angle. Well, as I said, that's going to occur in the second quadrant. It's going to be 180 minus 38.6821. So what is, I'm going to hit that a few times, 180 minus 38.682188. And this is the second angle. This is the second angle. So second angle 2. Angle 2 is equal to that. Now, I'm going to also see if that can be determined both by taking 2 pi and subtracting this, or 2 pi and subtracting that, after I convert this to radians to see what that is in radians. Well, how do I convert that in radians? And you don't have to convert it to radians. You just keep it an angle if you want. Essentially, I have the 2 angles right here, but I want to show you that you can figure out your radians first if you wanted to. So if I wanted to figure that what that out is in radians, I would divide it by pi, in degrees, divide by pi and multiply by 180. Oh, that's not, that's turning it into degrees. So I got to clear. I got to take my 141.317812, and to convert it to radians, I divide by 180. And by the way, there's my pi radians. Copy. This is how many pi radians it is. And you don't have to do this. I'm just doing it to show you. So it's that many. Wow, this all gets converted to 1. That many pi radians. And if I divide the pi out of it, angle 2 is also this many numerical radians. And it's hard to fathom what I'm doing here, but that's okay. And you can see that I actually might have, yeah, actually the first one's the numerical radians and the second one's the pi radians. So I'm just going to be that. Yeah, this one is the pi radians, so let's just say that's 5. Pi radians. And this first one is radians. Let's see if that, so I divide by 180. Actually, 141 should have just been 141 divided by 180 should have been in the pi radians. Yeah, that is the pi. The first one is the pi radians. The second one is just the radians. That's 0.78 of a pi radian, and the second one is simply that many radians. When I multiply, actually no, it should be 0.78 times pi to figure that out. And the second one is, I'm screwing this up, so it might be better just to work in degrees. And the second one is this, 2.466. 0.466 radians. Now, let's just see by looking at this original one and subtracting from 2 pi. So this one here is pi radians. So if I take 1 pi and subtract it, I should get that. And sure enough, 1 minus that is indeed that. So you can see that's in pi radians. And then if I take this and subtract it from 1 pi, which is 3.14, I should get 3.14 minus about 0.7. I should get about 2.6, or 2.4 rather. So 3.14, let's just do it with a calculator. 3.1415, which is pi, and I subtract 0.675132, I should get the second one, 2.46638. So this, indeed, this is the numerical radians, this is the pi radians. And I did it 2 different ways, by converting that angle or by taking 1 pi and subtracting and adding, subtracting that. Let's just ignore all that and just stick with the angles. So right now, I know that angle 1 is equal to that many degrees and that many degrees. So those are the 2 angles. It's at this stage that you then bring this back. But notice it's got a pi in it. So really, I should convert one of them to the pi radians. So I'm going to just use the first one. Angle 2 is this many pi radians. How did I get it? I simply took this and divided by 180, and I got this many. Oh, I deleted the wrong one. I got this many pi radians. And then this one down here is simply 142 divided by 180, and I got this many pi radians. Okay, let's see if we set this to either one of these, it should work out. So we'll start with angle 1. If we set that to that, what's our first step for getting, we got to get this bracket all alone? Well, it's being multiplied by this thing, so we're going to multiply by the inverse on both sides. When I multiply by the inverse, sorry, I accidentally multiplied by the main thing. When I multiply by the inverse on the left side, it cancels out, which was the point. And when I multiply by the inverse here, notice my pi's cancel out. That's why I left the pi in there. Okay, so I'm left with 4 times this is equal to t minus 1. So if I'm going to get rid of this minus 1 here, my time is going to be this. Whatever this multiplies out to, 4 times this, we no longer have the pi, radians, plus 1. And the radians will disappear because it's pi radians down here, and the word radians disappears. So it's just going to be 4 times that plus 1. It'll be time in seconds. So what is 4 times 0.214? I get that. Plus 1. So according to this, as I predicted, it happens very close to 2 seconds. So time 1 is going to be, time 1 that this occurs is going to be this. So I found the angle, I made it equal to the internal thing. I found the angle in pi radians because my internal, if you look at your internal adjustment, it's all being done by pi radians. So I know I have to work in radians, preferably with a pi in it. And then I was able to find out time 1. Well, time 2 is going to be equal to this one here. So we then take the internal clock that we have here, that we put aside, and we make it equal to the second value right here, like that. So I'm going to just get rid of everything else. So I make this equal to that. So the first step is multiply both sides by 4 over pi. Both sides 4 over pi. And these two cancel out, become 1. I'm left with t minus 1 is equal to this. And then notice on the right side, the pi's cancel out. Pi radians, pi radians. And I'm left with 4 times this, and then I've got to add this one. So again, this becomes all 4 times that, plus 1. So now I have to figure out what 4 times this is, plus 1. I hope I didn't get the same thing here. I might have gotten the same thing. 4 times 0.7851. No, it's much more. Plus 1. And time 2, I discover, is indeed roughly what I suspected. Time 2 is equal to 4.1 seconds. First 1 seconds as well. So that fits in very nicely because I remember 5 seconds it reaches the halfway point, and I said around 4 and around 2. So I'm very close with this. So I believe the answer to this first question is it in the first 8 seconds it dips through here at 1.85 and then comes back out of the water at 4.1. I'm going to put this into Desmos to confirm my answer, but go back here and notice it says but in the first 24 seconds. Well, it takes 8 seconds to go around once, 16 seconds to go around twice, 24 seconds to go around 3 times. Each time this happens, I'm adding 8 seconds to the new period. It takes 8 seconds. So to figure out the other 4 times that this happens, time 3, okay, time 3 is going to be time 1. Time 3 is going to be time 1 plus 8 seconds. That's all you do with that. It happens the next cycle over, which happens to be 1.8596 plus 8, which happens to be 9.8596. So I just really just add a 8 in front of the number. Right? That makes sense. Good. So that's time 3. Time 4 is going to be time 2. Time 4 is going to be time 2 plus 8 seconds. Time 4 is going to be time 2 plus 8 seconds, which is 4.1404 plus 1. So time 2 happens at 5 points. So it repeats essentially every 8 seconds. Now, time 5 is going to be time 3 plus 8 seconds, or 8 seconds, or it could also be time 1 plus 16 seconds. It doesn't matter which one you use. But I might as well use time 3. Looking at time 3, it was 9 point something plus 8 seconds is that. Seconds. And notice I forgot the 6 each time because I had a 6 in the original one. And time 6 is equal to time 4 plus 8 seconds, which was 5.1404, which becomes 13.1404. So there we go. I have all the same times. The only thing I kind of forgot was this here. But everything else is right. And seconds, they're all seconds. So now I have time 1, time 2. I forgot, there's time 2. I forgot to keep a copy of it right there. Oh no, it's up above. So there we go. Now I have all 3 times. Now all we have to do is take Desmos, replicate this exact equation, and see if indeed it goes down below the y is equal to 0 line, the x-axis, on these times. And if it doesn't, we know we did a calculation error. So you pull up Desmos, and you go y is equal to, so f of x is equal to minus 4 sine And then in brackets, it was pi divided by 4, I think. And I'll just keep it as x instead of 1. And then the whole thing was elevated by, let's see. The whole thing was elevated by 2.5. 2.5. Okay, now I'm just going to notice the x-axis. I'm going to put in my normal axis. There's what the wheel's rotating around. But I'm also going to put in the y is equal to 0 line so we can see it clearly. And hopefully, I'm going to also set my x to be 0 or smaller or equal to x smaller or equal to 24 so that we get 3 full cycles. There we go. Notice that the cycles, and actually I have to adjust by 1 because, they only said the first 24 seconds, so it doesn't really matter. Technically, I would make it first 25 so that I get a complete cycle, and I would start it at 1, like that. But that's okay. Let's see if I get the right times. So I got at time 1 second, yeah, but when does it dip into the water? At the green arrow. 1.86. So I'm going to just click all these values and see if I got them. Those are the first 4 values. Boom. I'm going to click them, copy them, and I'm going to take the image here and see if I got them. And just shrink. Okay. According to me, time 1, and just ignore that. That's when it starts. Time 1, 1.86. Yep. 1.8596, 1.86 seconds. Time 2, Desmos is just rounding up visually. Time 2, 4.14. Got it. Time 3, 8 seconds later from time 1. 9.86. Got it. Time 4 is 8 seconds past time 2. 12.14. Oh, look at that. I made a technical error. So 4 plus 8 is not 15. See, I added 1 here by mistake. I made 8. 4 plus 8 is 12. I should have spotted that visually, and you probably did. 12. So I accidentally put 1 here, but I should have been adding 1 full period. Even though I got it correct here, I retyped it wrong here and then carried out the incorrect one. So that's 12.14. I would have lost points on the test. And then this next one, time 5, 17.86. Very good. Notice I made the same mistake twice. I had to add 8 to that, so I'm going to get 20.1405. Even though I correctly added 8, I added 8 to the wrong time. So 20.1405, and sure enough, there it is. So other than not being able to add 8 properly, and you can see where just one error screwed me up, I indeed got the correct times. And it's all about getting rid of the internal adjustments to the angle, figuring out the actual 2 angles, because it always crosses the sine curve at 2 angles, and then understanding the question wants me to describe the next 3 moments in that equation. Very interesting stuff, very useful skill set to have, because if you can do those, you can do pretty much any question. So the others are similar, and I think I'll just end it at that.